Hey everybody, welcome back again for a great edition of First Fundamental Theorem of Calculus. This is First Fundamental Theorem of Calculus Part 2, and we were left right here with our absolute value. Did we find much antiderivatives of absolute value? Oof, I don't remember. But the good thing about this is we can do this, but we have to remember what the definition of absolute value is. Let's graph this thing first. What does absolute value of x plus 1 look like? Well, where's our vertex of that absolute value function? -1 would be correct if that's what you thought, and then we have something that looks like this. And we are trying to find the area from -2, which is right here, all the way at 3. 1, 2, 3, all the way there. So this is what we're trying to, this area, I'm just going to put a vertical line there and there. This is the area we're trying to find here under absolute value. But the way I have to do this is I have to break it up into two separate antiderivatives or definite integrals. I have to break it up into this part, and I have to break it up into this one. So where the line is going down to the vertex, that is going to be one part. Now what does that line really look like? Remember, the absolute value is just made up of two straight lines. This line actually is -x minus 1. Negative slope, and then if I continued it through to the y-intercept, it would be -1. And this line is positive x plus 1. Because the absolute value could be the positive of this, but since the absolute value means, or when you evaluate it, becomes positive, this can also be the opposite of this, -x minus 1. Alright, so now we have to break this integral. We can't just go from 0 to, or -2 to 3. We have to break it up into two parts. So we have to go from -2, that's here, -2 to -1. But we're only dealing with this curve, this graph of -x minus 1 dx. We have to add to that area the rest of it from -1 to 3. Oh, sorry, it's supposed to be -1 to 3. This time it's going to be x plus 1. That's the part you got to think about, dx. Now we do what we always do. We take the antiderivative, -x squared over 2 minus x, and then applying the first fundamental theorem of calculus, we put the lower bound and upper bound in there, and we just add to it to this guy. This is going to be x squared over 2 plus x from -1 to 3. What I'd like you to do is evaluate that. Take a moment and do that. You can pause the video and actually go through the motions and see if you actually get the right answer. I'm going to continue going, but I'd like you to pause it and see. I know some of you will say, I'll just watch. But I'd like you to try one on your own. I'm going to move some of this up so I have some space. Wow, that's a lot of space. So I'm going to move that up there, and this over here, and this over here, and that there. There you go. Let's see if I can move all this up. Oh, wonderful. Alright, so now I'm going to plug in -1 here, so it's -1 squared over 2 minus -1. That is that, the upper bound being put in there, put parentheses around it all, and subtract from the lower bound being put in there. Okay, we're going to get those values, and then we're going to add it to doing the same thing on the other side. 3 squared over 2 plus 3 minus -1 squared over 2 plus a -1. Whoops, there you go. And then you come up with the math and actually do the arithmetic. So this, what does this become? This becomes +1 over 2. It's negative though out here, so -1/2 plus 1. So what does that become? +1. So that becomes 1/2. I'm just going to write it up there. Minus, what does this become? 4 over 2, which is 2, -2. That becomes 0. That works nice. And then here we get 9/2 plus 3. So 9/2 plus 16/2, or 9/2 plus 6/2, which is 15/2, minus, again, this negative is not, this is now being squared. So it's -1 squared. It's 1/2 plus a -1. So 1/2 plus a -1 gives me a -1/2, which makes this positive 1/2. I know I'm kind of talking it through. So then the answer is 1/2, that would be for that little area right there, plus 16/2, which is 8. So 1/2 plus 8 is 8 and 1/2 as my area. I know I went a little backwards there with that, but that represents the area under the curve of this absolute value function. Okay? Let's do one more example in this part. Ooh, look at this. We have the antiderivative, I'm sorry, I keep saying that, the definite integral from 0 to 3 of x times x squared plus 4 dx. Right away when you see this, you know what you have to do. You have to take the antiderivative. Now, I'm actually going to make this a little bit more difficult. Put a 4 up there. Otherwise, it's just too easy because you could just distribute it. And my intention was to do what? To have you use a special rule known as u substitution. Yep. And there's my inside function, my u. Here's my du. 2x dx, right? There's no 2x, it's just an x, so I have to multiply both sides by 1/2 here. And then I rewrite my integral as 1/2 u to the 4th du. Cool. And now let's take our antiderivative, u to the 5th over 5. If you notice, I'm not putting anything here and here, I'm not putting anything here and there yet. I'm not doing that. I keep doing that. I'm going to erase this and start it over again here. So I'm not putting lower and upper bounds yet, and I'll tell you why in a second. So 1/2 u to the 5th over 5, okay, which is equal to, we'll just say it, u to the 5th over 10. Now I can put that x squared plus 4 back in there, and then do my lower bounds, and that gets... Look at that, x squared plus 4 to the 5th over 10. We can do this. Ready? From 0 to 3. And then we can do 3 squared is 9, plus 4 is 13. 13 to the 5th power, divide by 10. Oh my goodness, you can do the thing for 0. We can do that because these values, 0 to 3, represent x values. There's another way to do it that sometimes is a lot easier. So I'm going to erase that. And you might have some trouble understanding this right now, but that's okay. We'll go over it again in class. Is instead of putting, we can't put 0 and 3 here because they're x's. Let's turn them into u's. How do I do that? I plug 0, this guy, and this guy into my equation for u. So I write u is equal to 0 squared plus 4, which is equal to 4, and u is equal to 3 squared plus 4, which is equal to 3 squared is 9, 13. And that becomes, 0 becomes 4, and this becomes 13. Then we can put in there 13 to the 5th over 10 minus 4 to the 5th over 10 and get that answer. Holy Moses, you say, well, that's still not, 13 to the 5th is pretty big. Just another way to do it. These values represent u's. They are in terms of u, this guy. The 0 and the 3 are in terms of x. So you've learned u substitution where you plug this back into, you plug the u, x squared plus 4, back into this. Sometimes it's easier to do that, sometimes it's not. I was just giving you another opportunity or another alternative to do that. And then you can come up with this answer and figure that out. And I'm not going to do that right now. You can come up with that answer, that area under that curve. Well, I hope you enjoyed this part 2 of the first fundamental theorem of calculus. Again, the new part is actually taking the antiderivative, the integral, and then just evaluating at the upper bound and the lower bound and subtracting those answers or those values to get that area under the curve. Well, I hope to see you in class, and Johnstone out.